So we're trying to point people in the right direction as far as what's expected of them tomorrow. And these are some of the things that we talked about. We're not concerned about electronegativities or things like that. That's maybe more for later on where it says begin chapter 6, which would be on Thursday. But that's more so chemical bonding, okay? That takes place with those dot diagrams. So when we talk about the Afabu principle, in common terms, it's just saying that electrons will start to fill orbitals or energy levels in the lowest possible manner that can receive them. So that's just something that just comes off the top of my head. The lowest energy level that can receive them. Think of that. That's why you have that slide rule. Yes?
I was just going to ask, on the test, like, if it's vocab, will it be like the actual definition of the slide rule, or will it just say slide rule?
It would say probably Afabu principle / slide rule. Something like that.
And then for like the thing, it would be like the lowest energy level.
Mm-hmm.
So whatever the slide rule is, that's the definition.
Right. So, and like I said, that's something that we just quoted off the top of our head. Excuse me. Okay. Okay, so an electron that occupies the lowest energy orbital that can receive it. Okay, that's what this is. Okay, that is on page 111. Okay, so an electron occupies the lowest energy orbital that can receive it. And that is explained by the slide rule. Then we went on and we talked about Hund's rule, which is on page 112. Okay? Orbitals of equal energy are each occupied by one electron before any orbital is occupied by a second. So sometimes what happens a lot is it doesn't make any sense when you read the actual definition.
Yeah.
But once you actually apply that for, we'll just put, let's see here, gallium and selenium, okay? So gallium has what atomic, I think it's 31, isn't it? Does that sound right? Yeah, well, zinc is 30, so gallium's got to be 31. So we don't have to do the whole orbital diagram for these. And for some people, it makes sense that the electron configuration and the orbital diagram are really intertwined with one another, okay? And this is why. If we were to do the configuration for gallium, okay, that means you're probably going to use an argon core, right? If you're going to take a shortcut, okay? So what that means is we're already up to 18. There's our argon. So what comes after? 4s2. And then we've got 3d10, right?
3D. I think so. That's 31. No, that's 30, right?
30, yeah.
Okay.
So we need one more.
So then,
Or 4p1.
okay. So one of the things we could say is we actually used both principles for that, because this is saying these two electrons occupied this orbital before this one. That is explained by this, the slide rule / Afabu principle. Then, when we apply Hund's rule, we said that these two concepts are really intertwined with one another. If we needed to find the quantum numbers for this, We're concerned about that orbital. Okay? So then, how many horizontal lines is that? Yes, what?
It's 4.
How many horizontal lines is that?
4.
How many horizontal lines is that?
7.
3.
15.
Never mind.
Okay?
Not even close. I thought it was 3F, 4F. Oh, it's not. Never mind then.
Okay? So I would expect that you know 2 of the 4 quantum numbers right now.
4 and
4 and 1.
4 is 1.
4 and negative 1.
4 and 2. 4 and 1.
4 and
1.
okay, so n equals 4 because of this. Okay, L equals 1 because it's in the p block. M is, this is where we say the electron configuration and the orbital diagram are intertwined with one another. That's the way I think that makes the most sense. So therefore, we have to just put our lone electron in there. M is a value of negative L to positive L. Here is our negative L, 0, our positive L. So M is negative 1, and S is
Positive 1/2.
1/2. Okay? So then I think the next one I said we would do is selenium. Okay? We don't have to totally reinvent the wheel here by starting over, because if we're going to do selenium, which is 34, okay, it's going to look pretty similar to this. Already up to 18.
4P.
Okay, so then we've got 4s2, 3d10, and 4p what?
4.
Okay, so once we start adding these in here, a lot of these quantum numbers, they're going to be exactly alike, except for S. That is done in the Pauli exclusion principle.
No, M is not the same. Well, because then 4. Oh, yeah. no,
Okay.
it is.
So now we've got 4 electrons to contend with. Okay, so, okay, hang on.
But it's a 0.
Okay, so we need to use Hund's rule, or the bus seat rule, to finish this. Okay? And if we're ever in doubt, we could say 34, oops, not that. 18 plus 2 is 20, 30, 34. That's what selenium is, so that's going to be correct probably. So therefore, we've got 4 electrons to do. Let's use Hund's rule to explain that. There's 1, there's 2, there's 3, and then here's our 4th one. And that's why we say each orbital must have an electron occupying it before it can pair up, just like sitting in your bus seats. Okay? So the technical term probably really, we get it, but when you apply it, it perhaps makes more sense. So, is 4, or excuse me, not 4, is N still the same?
Yeah.
Yeah.
Is L the same?
Yeah.
Is M the same?
Yeah.
What about S?
It's negative 1/2.
So that's, oops, so that's an example that is that Pauli exclusion principle. It's just, even though you could even put them next to one another, okay? So we just thought, well, let's pick a little further down the road and do selenium. So what about if we did germanium? Is that, yep, that's right next to gallium.
Germanium.
Okay? So therefore, if this is GE, like G, this is fun. I know, right?
Yeah. It's really fun.
Yeah, we'll keep going when everyone gets up off the floor from laughing. So. Or maybe they're crying. I don't. Oh, that's right. There's no crying in chemistry.
Literally. Right.
Oh yes, your eyelashes will be clean.
They will be. And they'll grow. Doesn't crying make your eyelashes grow?
I think it does.
Yeah,
Or helps it in some way?
they do. Because of the salt.
See, that way.
Salt usually hinders growth, not accelerates it.
Well, in your eyelashes, it makes it
It dries them.
better.
It grows them.
Grows them.
Like magic.
I find that very hard to believe.
What?
Well, you should believe it. We're scientists.
Yeah, and we're girls.
So what are your eyelashes?
Well, the second part, yes. The first part, well, yes, you're on your way to being that, but a scientist, but
Then why aren't they just
Yeah.
always long? Do they-
we'll just take your word for it.
We
Okay,
don't cry.
so we said germanium. So that's 32.
What the stupid.
So again, all of this is still the same except for this one.
M and S.
That will be 2. So now, is N the same?
Yes.
Is L the same?
Yes.
Is M the same?
What's 0?
Okay?
Why does it go?
So we need to take that one out, and then this one. You could say, well, maybe that stays. You got 2 electrons in there. But that's what's explained by Hund's rule. You have to have these occupied first. So now, okay, that's the same, that's the same. This is now 0. So 4, 1, 0, plus 1/2. So no matter how you do these, you're not going to have 2 elements with the same 4 quantum numbers. They can be pretty similar, but not identical. Yes, what?
Never mind.
Okay.
You're right.
And this is called orbital diagrams.
Oh.
Orbital diagrams are these right here.
Orbital, and then the electronic.
And these are configurations.
And then the Bohr models. are
Bohr models have the numbers with the electrons circulating.
Oh, yeah.
The top.
That's what these are. Okay.
Call us D1 scientists.
D1.
Yeah,
Okay. I hope it's division, not duh. It's division.
it's division.
Yeah.
Divisioning.
Yeah.
Sciences.
You know, it's kind of rather odd that, well, I suppose when you look at national security and you look at, what is it, you have DEFCON 1 to 5 where DEFCON 1 is pretty serious. DEFCON 5 really isn't as serious. So when you say Division 1 or Division 3 is not as highly ranked as Division 1.
Yeah. So that's why we're D1.
All right, so you're D1.
Scientists, yeah.
All right. Well, we want you to be prepared no matter where you go in this immediate vicinity. Okay. So one of the things that can happen, okay, if we're going too fast and we're not paying attention is, for instance, how many electrons can each period technically hold? Not block, but the entire period. Some, that's true, but not all of them.
A lot.
Oh.
Now, remember, you're saying block. We're saying period. That's all the way across the table.
So,
Adding like 6 and 2.
If each, exactly. So
So 18.
the first energy level holds what? Okay. The second entire energy level,
would it be 7? Well, not that, but like
Or 10.
3,
Going across the 6.
4,
2.
5, 7, 8, 9, 10. Oh, God.
because the second energy level has the S block and the P block together. Then, when you go to the third period,
It's also 8.
no,
Yeah.
no,
1, 2, 3, 4, 5, 6, 7, 8.
no.
It starts at 3D.
What the skibbity?
So 18.
Okay.
Oh.
Then the fourth energy level,
18.
no,
Oh, it's F.
Uh,
So 30,
32.
32.
32.
right. So that's one of them things to where you're probably going to want to read that carefully.
Oh, so that's going to be on the test?
Maybe.
So wait, what's the question? What is it? How do you word it? Oh, don't read it. Never mind.
You have all the tools that you need right here.
Yeah, it's not there. I'm just kidding. I'm just kidding. It's there somewhere.
Oh, sure it is.
That's why, yeah.
Yes.
I can pull my water.
Yes, ma'am.
Can I fill mine up too? Wait, are those the periods we just talked about?
Those are the periods, yes.
Sorry, I know. Fill mine up.
Never mind.
Hey, I'll pull mine up as well.
Jake, we need yours too.
No, we're pretty good. Think
You
so.
want ice?
Yes.
All right.
Now, the bird.
Anything else?
Bonus questions, please.
Oh, why?
Pretty quick.
Because
I'm gonna need it.
Because it will ace my test for me.
And really
Well, if you
quick,
ace
right?
it, then what do you need them for?
In case I don't get the vocab, which
Okay, so in case you need a little bit of context here, typically when, I don't know if it's superstition or people will pick their number because that's maybe what they felt they had success with. So with Aaron Rodgers, we could say that's nothing different. But when he decided to leave Green Bay, went to the New York Jets, he could not have number 12 because that number was, I'm guessing it was retired. Okay? So who is it that had uniform number 12 for the New York Jets? That's why he couldn't have it. That would be my presumption, and that's what we're going with. And then before the Houston Texans, okay, that's what the team is now in Houston. What were they known as before the Texans? That's what this one is. Okay, that's all I have. We'll catch up to you next time.